We're talking about force. The definition you all came up with was that force was what? One of two things. Pushing or pulling. And you said it's acting on something else. So there is something that is causing something else to do what? To move. It's producing some sort of movement, right? It is the change of energy in something, right? You're actually giving, you need energy in order to make that force. I would agree with that consistently. Yes. But we're doing something to someone else, right? Or something else. If you want to go, we're in chapter 4, is where we are, if you have your textbooks. There's a couple of definition pieces that we need to get settled first before we go too far. Let's use this lovely health book. Okay? Can we stand up and you guys kind of gather around a bit? It's much easier if we're all together. Or at least come so you can see. If you want to stay sitting, I'm fine with that. But come, there's going to be little motions, little things we're going to do together. So I'd rather you be reasonably close here. All right. We're starting off with this beautiful health book sitting on the table here. All right? We want to define our system first. Our system means all of the stuff that are interacting, the objects that are interacting together. Okay? So, let's take, what is my system when I'm looking at this textbook sitting here on the desk? What's my system? What pieces are we looking at? What are the objects we're looking at? The table, the textbook. Okay. Is there anything else that's interacting with this thing? Okay, so the table's on the floor. Okay. What else? Okay, there's some air that's actually standing on top of that book. I would agree. There's actually a mile plus of air on top of that. Okay, there's other objects. We're going to exclude. Are you comfortable right now? Because there's lots of other things on this desk here, right? There's my book, there's some weights, there's a controller. We're going to exclude that from our system right now. Is that cool? And we're looking just at this. Okay? And again, this is the key piece, is when you're talking about forces, you have to define what is your system. What are we looking at? Okay? There's one more thing we haven't mentioned, though, that is affecting this book. Gravity. Okay? And you say, well, wait a minute. Because she's got that number memorized, which is well done. But what's causing that gravity? Oh, the Earth. The Earth is causing the gravity, okay? So we have to include the Earth in our system, right? If I'm going to talk about gravity, I've got to include the Earth. Are we cool? All right, so let's talk about the forces. What forces are actually working on this textbook? Give me a hand. What forces are working? Remember, it's a push or a pull on an object, right? Pause. Is this object moving? No. So does that mean there are no forces on it? Ooh, good. It just means there's no net force. Net force means there's some force that actually is overcoming other forces. Okay? Are you comfortable there are forces working on this right now? But it's not moving, right? There's no push or pull you can see. So therefore, all the forces cancel each other out. Does that make sense? Because how do I know all the forces are canceling each other out? It's not moving. Because a force, if I have a net force, there's a push or a pull. It's actually causing motion. Are you with me? So let's talk about the forces. What forces are happening on this book? Give me a hand. Tell me. What's happening? Gravity is pulling in what direction? Downward. Okay. But again, this textbook is not moving. The table is doing what? Pushing back upward. Anybody know what we call that? I'll be impressed if you know. There's a name for it. Anti-gravity. That's not it. The normal force. It's a weird name. The normal force. The normal force is a force that's perpendicular to a surface. Yeah, right? Your legs. Okay, sure. When I'm standing here on the floor, right? My weight Gravity is pushing me down into the floor, right? But the floor is pushing back up. That would be the normal force from the floor. Yes. Okay? And are you comfortable, guys? If we let's put some forces here. Okay, so here's my book. Okay? This is the force of gravity. All right? And if we say that there's a force that's opposing that, if we're using vectors, right? That's what this is, a vector. What must I do with these two vectors? They must be opposite direction, right? Cool. And what else? Equal in length. Yeah. Mm-hmm. Absolutely. 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 Yeah. So this textbook, right? There's not enough mass, there's not enough weight force of gravity pulling down to overcome the surface of this table, right? But if I were to take and put your car on this table, right? It would break, right? It would have more mass than the surface can take. Okay? That's not saying your sister is heavy, it's just saying that she has more mass than that surface could handle. Yeah. Absolutely. Yeah. Yeah. Right. My father, the same thing. When I was about 10 years old, actually a little older than that, he was up in our attic. We were hanging a ceiling lamp, a ceiling fan, and we had to walk because the hole was in our garage, the entrance to our attic. And he was walking, and he took his flashlight up to look for the hole instead of looking at the beams he was walking on, and stepped right through, fell 10 plus feet, cracked his jaw on the hitch for our camper. He has no bottom teeth almost because, again, he knocked all that stuff out. He could have died, frankly. It was lucky he didn't. Lucky, in quotes. It was certainly a miracle he didn't. Okay, what other forces are acting on this? Well, there could be. I mean, right now there's really not. Ooh, I like that. I like that. Okay, so let's say that I am actually putting a force. You're right. I'll go with that. What force am I putting on this thing? Like, why? My gravity. I'm a little smaller, thankfully. Okay? Yes. So I am putting a little force on here. So we'll put Mr. Hess's force. Cool. This would be the force of Hess. I like it. Okay? So what is overcoming that? Like, in other words, why doesn't this textbook just go flying over and hit Kirsten right in the face? Okay, so Kirsten's, but she's further away. Are you comfortable? And I am larger than she is. Oh, but what's opposing it? It is affecting it. It does. It does. Okay. But what is causing that to resist my movement? I agree. I hear you. I agree with you. But its force would more be coming onto me. Does that make sense? It's pushing against me. It's pushing me away from, actually pulling me toward it. Okay? But if my force is trying to draw it this way, what is resisting that force? And actually, I should change this direction because I am not pushing on the book. I'm actually drawing the book closer to me, right? Sure, yep. But why doesn't the book then come flying toward me? It does, but again, that would be pulling me toward it. That wouldn't be opposing mine. Say that again, Kirsten. Are you comfortable that this book doesn't want to move? There's actually forces between the book and the table that are holding it in place. And we call that friction. Okay? Now, is my force that I'm producing gravitationally enough to actually pull this book toward me? No, it's not nearly enough. Okay, its mass is much too big for my little tiny bit of gravity. Okay? But what's opposing that motion is that force of friction. Sure. Yep, the force that friction produces is greater than my gravitational force. Exactly. I can use my muscles and create enough force to push that book off the table. Right? I can overcome the frictional forces, right? Are you comfortable? I can also push on this where I'm actually pushing it sideways. Like I'm literally putting a force on here, but the book's not moving. Or my force is not enough, right? Yeah. I'm thinking I'm not too weak. I'm just kidding. Okay. Question.
So, if your gravitational force is too small,
Mm-hmm.
would you say that a building gravitational force is bigger?
It's bigger than me, certainly.
So, how come this is not?
We'll learn about this. I don't want to give you the equations now, but basically the amount of gravity that we can produce is like a 10 to the negative 20. It's a tiny amount of force.
What is something that we can actually track? Like, is there a particle small enough for that?
Not that I'm aware of. Because again, we produce so little. And if you're talking about, if we're going down to the size of strength of field that we can produce, the other things around us weigh much more than we do.
Is there any way to maximize our strength? Like, is there...
Not that I'm aware of. Not that I'm aware of. In other words, can we make the force and move things? Not that I'm aware of.
Is there anything like not like made purposely to move, but something you feel
That could move based on our gravity? Not that I'm aware of. It's too weak. It's too weak to actually do something worthwhile with. Matt, your question.
So to break the friction, you have to put the book straight out. You have to break the friction.
Okay, so are you comfortable that friction, and we're going to talk much more about this, but friction is the rubbing of two surfaces together, okay? So if I do this, I'm not overcoming friction, right? I suppose there's a little bit of actual attraction between the book and the table. When I lift it up, I am breaking that, but it's very, very, very small. Friction is more this moving parallel to the surface. I would be overcoming gravity to pick it up. That's exactly correct.
So is there a difference between, like, friction and, like, something being magnetic?
Sure, that's a different force. Yep, that's electromagnetism, a different force. Yeah. Are you with me, guys? Okay, so when we talk about our system, right, we have to make sure we include all of the pieces that are affecting this. Now, are you comfortable? We don't have to always look at every single force that's affecting this thing. We can just define our system as being simply the book and the table, right? And just deal with the normal force and the gravitational force, and we're done with that. Does that make sense? We don't have to always talk about the air and the gravity and the this and the friction and that. Does that make sense? We can define our system how we want it to be. But we have to make sure we remember, hey, there are other forces that are present there. Are we cool? All right. That's good. That's good. When you actually push something, that's called a contact force, right? I'm contacting the piece. If we're talking about gravity, is the planet actually physically coming and grabbing Clayton and pulling him downward? No. We call that a field force, right? It's a force that goes over a distance, rather than I have to actually be in contact with him to put the force on his shoulder from my punch. Does that make sense? Okay. And again, net force is the key. Let's show some net forcingness. I'm nervous. Ben, why don't you come right here? Nick, why don't you come right here? Okay? Yep. I want you, please, to push this way. I want you, please, to push that way. And I want 0 net force. Oh, I don't want the table to move. But show me some force. Pushing that table. But come on, give me some force. Give me some force. Yeah, so they're pushing, right? If we were to draw those arrows, there's some pretty big arrows going here, right? Oh, they're trying to overcome, right? Good, relax. Good job, thank you. Thank you. They're pushing, right? They're pushing hard. So I want to make sure you understand, net force doesn't mean there's a little bit of force. I mean, these guys are pushing decently hard, right? Veins popping, faces reddening, right? But did the table actually move? There were times that it was moving a little bit one way or the other, right? When maybe Ben had a little bit more than Nick, maybe Nick had a little bit more than Ben. But overall, the net force was 0. Why? Because the table's still in the exact same place it was. Sure. So they could have potentially pushed so hard that the table itself couldn't withstand those forces, and it would have crumpled, right? But thankfully, they were kinder to my table than that, right? Sir.
If like we had a thin like outer crust, like if the inside of the Earth was like hollowed out,
Mm-hmm.
like the Earth would just crumble under the sun.
I do. Yeah, because we're actually, gravity is drawing everything to the center of the planet, is basically how that works. So sure, it would.
So it'd just be like a random like section, like point of gravity that was like so large. Is that like what they call gravity well?
Isn't that a black hole becomes when it's like too much? Is it?
Yeah, the point of a black hole is it just taking all of the mass and putting it into a tiny something like you could hold in your hand. The mass of a whole planet right here. So that just is it's too much. It's too much mass in too small of a place. Yeah, just basically is pulling everything into itself. Yeah. Your question about this gravity well piece, again, think about if you were to dig a big deep hole, right? If there's nothing supporting this top of the hole, right? It's going to fall into it, right? So, because gravity is still trying to pull it down toward the center. There is not like some magic place in the center of the Earth where that's where all the mass is stored. It's just the point it's all being drawn to is that center of the Earth. Sure, based upon the mass. So are you comfortable that the center of our planet is not solid? Like we have a couple of miles worth of solidness going down, but then it's mostly molten, it's liquid, right? So depending on how that's moving around, there is slight fluctuations in our gravitational field, yeah.
If we like discover something where we can like shift it, yeah, could we shift the axis of the Earth?
We could, theoretically, sure.
Do you think we'd be able to do it?
I don't think so. It's too much mass. There's this whole physics problem of, if everybody in the entire world got together in one little spot and jumped at the same time, right? Could we shift or move the world? It's still not enough mass. The Earth is significantly larger, even than the billions of people we have. It wouldn't affect it. It would be like a little gnat landing on you and jumping up and down. It doesn't affect you at all, other than you want to smash it.
Well, they said it would like speed up the Earth by 0.0.
Tiny little bits, sure. Tiny little bits, sure. But you wouldn't actually have any theoretical or purposeful practical uses. And plus everybody would die because there wouldn't be enough resources for us all to live in that little area.
And it would take years to get it.
It would be a very difficult problem to actually get that to happen. Cool. Are you with me, my friends? Forces, right? Okay, let's play a little bit here. And I apologize if you're watching this on TV. I wish we would have filmed this instead. All right. You'll have to come a little closer because all I have is this for you to see. Okay? So are you comfortable? This is what we call a spring scale. Okay? There's a little spring inside here, right? And as I pull down, right, it shows how much force I'm producing. Now, on the left of this scale, it says grams, right, which is a measure of what? Of mass. Okay, remember mass is different than weight. Mass is the amount of stuff you got, right? The amount of material that makes you up. Weight is how gravity, the force that gravity is putting on your mass. So are you comfortable that my weight here on this planet, let's say, is 220 pounds? If I go to the moon, does my mass change? No. I'm assuming I just went there immediately, didn't have to walk there or something. Okay? My mass doesn't change, but will my weight change? Yes. Why? There's less gravity. It's about a fifth, right? So I would go from weighing 220 pounds to weighing 40 pounds. I mean, it's a nice weight loss, right? But nothing changed with my mass, right? You had a question or no?
So shouldn't we really like measure ourselves mass then, not weight?
I hear you. For the most part, in the world that we live in, the gravity is pretty much the same everywhere. There are small little differences between here and, let's say, Denver, Colorado, because you're further up in the air, but it's not significant enough to really matter. There you go. Yeah, you would actually weigh slightly less. Well, BMI is looking at a different something. There are problems with BMI as well. BMI, body mass index, is looking at the amount of mass based upon your height. That's really what it's looking at. It's just correlating those two things to give you a number. There are problems with that because if you have a ton of muscle actually weighs more than fat does, right? So I could be the same weight as 220. There are the number of NFL players who weigh 220. Are you comfortable? They weigh usually more than that, but let's take some receivers, okay? Right? They weigh 220. So does that mean we would have the same body index? We have the exact same BMI if they're the same height as me. But are we the same healthy-wise? No way. They're way healthier than I am, right?
Remember 8th grade, coach was trying to explain to us, he told me I would have failed because, like, from my height and age. Oh, yeah, that's true.
Right. And again, but that doesn't mean you're unhealthy. Yeah. So BMI is a good piece to use, but it's by no means the perfect something. Okay, we've got into a little tangent here. Let's come back to, welcome Ronnie, glad you're here. Let's come back to moving this thing. So we have grams on the left. On the right, we have another set of units. Can you read what that says? It's called newtons. Newtons are a measure of, anybody? A force. Okay? Newtons are a measure of force. So, if I were to take, if you would pull on that, just the end of that, I'm going to hold here. Good, don't break it for me. Are you comfortable that based upon how much I pull, I can add more or less newtons here, right? If I'm pulling down 7 newtons is the same amount that a 700 gram mass would have if it's hanging. Let me show you. So if I go to 5 newtons, that's how much force I'm pulling. If I take a 500 gram, which this is 500 grams, and we hang it on there, it should read 5, yeah?
Almost.
Pretty close? Good. The good news is that I just need to adjust this a little bit. There we go. Does that make sense? And the reason why is because what force is pulling this weight down? Gravity. What's the acceleration of gravity? 9.80 meters per second squared. If we round that, what number would you say? 10. So 10 times the mass, this is 500, times 10 would be 5,000, right? But newtons is measured in kilograms, not grams. Does that make sense? So therefore, 5 newtons is what I get here. When I take that 0.5 kilograms, 500 grams is 0.5 kilograms, multiply it by 10, I get 5 newtons. Sure, you're right. It's slightly off. But for the purposes we're using here, it works. But you're correct. It's not exact. Are you with me? So force will change based upon the amount of mass that's present there, right? If I were to, instead, this is going to basically overwhelm this guy because this is a 1 kilogram mass. It should take that all the way down to 10. Or pretty darn close to it, right? Does that make sense? All right, if I want to get this car going, okay? I'm going to give some resistance here, just gentle, because this is very easy to roll. Hang on. Give it a pull and see if you can't see. Watch this, and we'll see if we can't see what will make this guy move. Go ahead. Good, come back. Can you guys see? Watch the arrow, the little indicator there. Go ahead and pull it. Is it measuring anything? No. And it's better if we start and stop, because there's actually more friction when you are getting something going than when you're keeping it going. We'll talk more about this. Try it again. It didn't hardly move, right? Why do you think? Is he putting a force on this thing?
Yes.
He is.
Since there's a friction, it makes it like...
Right. Because what would keep this thing from moving is the friction between the tires and the surface, right? But in this case, it's such a little tiny amount. Can you see that these tires are super duper thin? Right? And they roll very easily. The point is, this is to reduce friction as much as possible, right? So that doesn't make too much difference. Okay, what if I do this? And I put some more weight on here. What do you think is going to happen now? Are you comfortable? It's going to take more force for him to get this guy going, right? Let's see if we can actually get a reading here. Gentle. Did you see any kind of movement in it? Try it again. There's not much, right? Let me give a little bit extra here.
Jump to like almost 10.
Do it again. Are you with me? So we're actually getting a little bit of motion here, but there's some force it has to overcome to get rid of me holding onto it before it will actually move. Okay? This car, it moves so easily. You know, it's too easy, to be frankly honest with you. Let's try this. I'm going to do it this way. I'm giving you some motion. The scale's moving a little bit. And it's that in that initial pull, right? Because we'll talk more about friction, that it actually is easier to keep something moving than to get it started moving. All right? So are you comfortable that force depends on mass, right? And it also depends on the acceleration of the something. Are we cool? Excellent. Are you comfortable we write that as an equation? That force equals mass times acceleration. Anybody know what we call this? Fama. It's called Newton's, which one? Second law. Newton's second law. This is one of those physics concepts that I should be able to burst into your bedroom at 3 o'clock in the morning and say, what is Newton's second law? And you should be able to tell me F equals ma. And then you'll probably shoot me or something. That's fine. Okay? But the point is, this is a basic concept in the world of physics. And again, what is the F? Force. What is the M? Mass. Listen, guys, it's not weight, it's mass. And what is A? Acceleration. Okay? What are the units? Let's talk about units. What are the units for mass? In this case, we're going to use kilograms. That's our standard unit we're dealing with, but it is grams as the base unit. What is acceleration? Per second squared. Don't forget that squared. Meters per second is velocity, right? And what about units for force? Is Newtonians. The Newtons. The Newtons. Are you with me? And what is Newton? Newton is actually what we call, it's a unit that we've put together. We've combined some things together. And I, for some reason, can't come up with a name of when we combine those things together. But a Newton is a kilogram meter per second squared. Right? Kilograms times meters per second squared. Kilograms, meters per second squared. Does that make sense? It's a derived unit. We're getting it from the combination of these other pieces together. Are you with me? Whew. So this is what we called which law? Newton's which one? Guacamole, thank you. So here was Newton's first, sorry I missed that, about inertia, right? The resistance to change. Newton's third, what's that? Ooh. You know this is equal and opposite forces, right? When I push against Matt, man, if I push against him, he's pushing against me, right? If I'm in space and I flick that car this way and it starts to move, what also happens to me? I start going backwards. Are you with me? Because there's an equal and opposite force. Okay? If you were looking for where these are in your textbook, actually the third one is not listed in this first section. I thought it was, but it's not. Okay? So we'll come back to that because that's coming later in chapter 4.
So that's the one that says like for every action there's an equal opposite reaction.
Exactly. For every action, there's an equal and opposite reaction. Are you with me, my friends? What I'm encouraging you to do before I see you next time, I would love for you to take a look, please, at 4.1 as well as 4.2. Okay? Because we're going to spend some time on some problems in 4.1 and 4.2 when I see you next on the moon day. Sound good?